Welcome. This is the set of notes for the second unit in our introductory course about relationships. The primary thing in our course and in all of statistics is to study how one variable relates to another. And so there is some special notation and some special definitions for this. The primary interest variable, the variable that we're trying to explain and understand what happens to it, it's called the response variable. This also can be called the y variable or the dependent variable. The variable that we're going to use to explain the response variable is called the x variable or the predictor or covariate. There's many names for this kind of variable. And we're going to be studying how the predictor variable explains the response. The primary graphical method for this is called the scatter plot. And so the numeric value of the response variable goes on the vertical axis, and the numeric value of a predictor value goes on the horizontal axis, and the numeric value for the response variable goes on the vertical axis, and many units are measured, and each unit that's measured has two of these measurements, one for the x variable and one for the y variable, and these pairs, when they're graphed, form a scatter plot. And so here's an example of one. Here our predictor variable is, well, our units are students, and we're testing their blood alcohol content, and we're going to try to observe, does their blood alcohol content relate to the amount that they drink? And the horizontal axis, or the x variable, the predictor variable, is the number of beers consumed, and the vertical axis is the blood alcohol concentration. And what you can do here is you can see in our little data sheet, you can see that student number 7 is shaded here, in a light blue aqua kind of color, and this student had 3 beers consumed, and their blood alcohol content was 0.07 milligrams per milliliter of blood. And so that would mean that their student number 7 has a blood concentration of 0.07, which would be right about here, and they had 3 beers. So this particular point corresponds to student number 7. Student number 15 had 1 beer consumed and a blood alcohol content of 0.01. And so that corresponds to this student right here. There's another student that had a whopping 9 beers consumed, and their blood alcohol content was amazingly high, like 0.19. Let's see, which student is that? That looks like that's student number 3, 9 beers consumed, blood alcohol content of 0.19. And you can see that each plot symbol here corresponds to a particular student, their combination of beer consumption and blood alcohol content. You can see from this pattern that it's pretty understandable that the more beer that's consumed, the higher the blood alcohol content. You'll also notice that, for example, when we consider all of the students that drank 3 beers, there's quite a bit of variation in the blood alcohol content. And so 3 beers, these 3 students consumed exactly the same amount of beer, but have very different outcomes, blood alcohol content outcomes. And that might be from size of the person to how much they ate, or just differences in how bodies process alcohol. And so you can see several instances where the same amount of beer produces a very different response outcome. In this particular example, we have a predictor variable that is the calories for some hot dogs, calorie content per hot dog, and we can see the vertical axis is the sodium content for some hot dogs. And you can see from this pattern in the scatter plot that there is kind of a relationship, that hot dogs that have more calories also tend to have more sodium. But it really isn't the case that one of these variables really could go on either axis. There really isn't some sort of causal system that calories produce sodium or sodium produces calories, and it's really not clear which one of these two variables should be on the horizontal axis and which one should be on the vertical axis. It's very much arbitrary in this case which one should be the x variable and which one should be the y variable. Another very common kind of data pattern we see is something that's called a time series, where a particular variable is graphed against time. And this is a very common data situation. The little example we've got here shows the price of oranges over time, 1992 to about 2002. And what you can see from this is a very kind of regular pattern that pretty much once a year we have a price spike in oranges, and about once a year, every 12 months, we have a low price area. We can also see that as time is going on, the price of oranges generally is going up, but you can see this very clear seasonal pattern. One of my favorite countries in the world is Australia, and I've visited it many times and lived there for a period of time. And here are some time series graphs for housing prices in various big cities in Australia. And you can see from this that a city like Darwin, this purple curve is showing very clear increases over time in housing prices, probably high housing prices, and that the prices are going up rather quickly. You can also see that Perth is this line, and Perth out in the western part of Australia also has very high housing prices, probably due to the big minerals and mining boom that's out there. And so you can see that over time, some of the cities in Australia are very expensive for housing, and prices are growing really very rapidly, but yet other places in Australia are much more modest price growth, like here for Sydney, and you can see other cities that prices are going up, but not quite so rapidly. When we look at a scatter plot, we would like to keep track of three conceptual items: a pattern's direction, and we would term or call these directions positive or negative association, a positive direction or a negative direction. A positive direction or a positive association would mean that as the x or predictor variable goes up on the x-axis, the y variable or response variable also goes up on the y-axis. A decreasing pattern would mean that as the horizontal axis variable, the x variable, would go up, the response variable would go down, for example. Form of the relationship is what kind of pattern in the points do we see in a scatter plot? Is it sort of a straight line, linear kind of pattern, or do we see curves or nonlinear relationships? The other thing we would notice is how much dispersion or scatter there is in the points. And so let's talk about some of these with some examples. So this scatter plot that's on the left would be an example of a negative association or a negative relationship. As the x variable is going up, the y variable tends to go down. And in the scatter plot on the right, you can see that it's a positive association. As the predictor variable goes up, the response variable tends to go up. Both of these relationships look like they are basically linear. There's no obvious curves in the scatter of points. And as far as the scatter of points goes, it looks like this graph on the right has more dispersion in the cloud than the graph on the left. Here are some examples of nonlinear form patterns, and you can see very obvious curves in the scatter plot, and these would be called nonlinear association patterns. Here are a couple of scatter plots that have no association or no evidence of any association between the horizontal axis variable and the vertical axis response variable. No discernible upward or downward trend in either of those plots. Here's a favorite data example of mine. This is about hamster hibernation, and on the horizontal axis we have the percentage of the daily life of the hamster spent hibernating, and so a 0 would mean the hamster is sort of never resting, never relaxing, always running on their bloody wheel, very hyper hamster. Up here on the high values, these are higher percentages of rest and relaxation for hamsters. Hamsters that would be out here on this level of the scale would be very laid back hamsters, and you will notice that there's sort of an even distribution across the restfulness and hyperactiveness of the hamsters. On the vertical axis, we have how long they live in days. And what do you see in this pattern? Well, what would this mean? Well, a point like this right here would mean that the hamster was very hyperactive, almost never resting or hibernating, and they lived only a few days, maybe maybe 100 days or so. This hamster out here is a very laid-back, restful hamster and lived about 1,600 days. You can see that there is some evidence of a positive upward association. Hamsters that tend to hibernate and rest and relax more tend to live longer. Hamsters that are more active tend to live shorter. You can see the cloud lifespan range for hyper hamsters is about 500 to 1,000 days. For the less active hamsters, it looks like it's between about 700 and 1,500 days, so generally a little bit more. Looks like there is a linear, sort of constant upward pattern, but lots of scatter. Here is a picture of my son's hamster, and here is a picture of a little hamster hammer. Is little mini-sized hammer for the hamster, and the overhead here is to think about, well, if we just gently clunked a hamster on the head with a hammer and knocked it out and had it hibernate more, would that mean that the hamster would live longer? And the answer is that these two things are not necessarily causally related, and that if I could clunk my son's hamster on the head and have it hibernate and rest more, that would not necessarily cause it to live longer. It probably wouldn't. And that's a general thing to know about scatter plots. Just because a horizontal axis variable might change doesn't necessarily mean there's a causal connection with age. It might be a more complicated process, just that these two things are related, not that one necessarily causes the other. Here's a very interesting scatter plot back from the year 2000 presidential election between the primary candidates. The major party candidates were George Bush, the younger, for the Republicans, and the Democratic candidate, I believe, was Al Gore. And so what we observed in that presidential election for the election returns in Florida was this very abnormal outcome in Palm Beach County, Florida. What's being graphed here is the county returns, number of votes for George Bush the younger, and the number of votes for presidential candidate Pat Buchanan. And what you can see in almost all of the counties except for Palm Beach is that counties that had more votes for Bush also tended to have more votes for Buchanan on almost a nice proportional linear scale. And that's just basically an artifact of the fact that bigger counties will have more voters, and the voters are proportionally allocating themselves between Bush and Buchanan and Gore roughly proportionally like this, and so it's not surprising to see this kind of pattern. The point that's way out here, I think, is Miami-Dade County, who are a very huge population, and so that's why they're out here on their own. But people that studied the election immediately noticed this strange result for Palm Beach County, and it was very surprising that they would have, well, what would you expect Palm Beach County for this many votes for Bush? We would have expected only about 700 or 800 values for Buchanan. Instead, we have almost 3,000, 2,000 more votes for Pat Buchanan than expected. Why did this sort of unusual data case occur? Well, it's from this very infamous ballot that was used in Palm Beach County called the butterfly ballot. And if you look at the construction of this, if you wanted to vote for George Bush, you would circle in a dot that would be right about here. If you wanted to vote for Al Gore, you would circle in a dot right about here. And unfortunately, they put a dot in between those that corresponded to Pat Buchanan. And so people with bad eyesight, like myself, or being very old, also like myself, would make mistakes and accidentally vote for Pat Buchanan, even though they were probably trying to vote for either Al Gore or George Bush. They would circle in the wrong dot, therefore producing abnormally high vote counts for Pat Buchanan. Basically, bad form ballot design caused that problem. Here's another politics election example. On the horizontal axis, we have the percentage in each state that voted for the Democratic presidential candidate in 1980. And on the vertical axis, we have the percentage in each state voting for the Democratic presidential candidate in the 1984 election. And each point on the scatter plot are states. For your political history, let me remind you that in 1980, the incumbent president was Jimmy Carter, and he was the Democratic candidate. So the Democratic candidate in the 1980 election was Jimmy Carter. He was running against Ronald Reagan, who eventually won that election, but that's who the candidates were. In the 1984 election, the incumbent president, Republican Ronald Reagan, was running against the former vice president. Under Jimmy Carter, the vice president was Walter Mondale from Minnesota. And so that was the Democratic candidate in 1984. What you can see from this scatter plot is a positive association. States that tended to vote Democratic in one election in 1980 also tended to vote Democratic in 1984. States down here that were Republican in one election tended to be Republican in the other. And so that is certainly a positive association. The direction, the form of the relationship looks like it's almost linear. So a linear relationship, positive association, and a fairly strong pattern. You will notice that there is a special mark out here for Georgia, and you need to keep in mind that Jimmy Carter was the former governor of Georgia, and Georgia is out here on its own for a reason. Why is Georgia where it is? Well, Georgia had a very high fraction of its residents voting for Jimmy Carter in the 1980 election, almost 56%. But in the 1984 election, Georgia was only at about 40% voting for Walter Mondale. So it's off out on its own here because Jimmy Carter was a very attractive candidate for Georgians, but Walter Mondale was not. And so that is why Georgia is way out here on its own. You can see that in the 1980 election, Jimmy Carter, Georgia had by far the most support for Jimmy Carter, much more than any of these other states. You can see that almost every other state went for Ronald Reagan. There was a much lower percentage voting for for Jimmy Carter in those in those states, and in Georgia a very high percentage. So you can see very far to the right in 1980, but not nearly as high support for the Democratic candidate Walter Mondale in the next election. I suspect that this state right up here is Minnesota. Pretty strong support for Carter, and the strongest of any state for Walter Mondale. You will notice that some of the states, including Georgia, have open circles, and the open circles stand for southern states. And you will notice that the southern states tend to have voting behavior a lot like Georgia did. Pretty high support for Jimmy Carter, but much lower support for the northern candidate, Walter Mondale. You'll also notice there's a dark state, full circle data point state right in here, right in the middle of the southern states, and that state is Arkansas. And so Arkansas technically was not a southern state because it's to the west of the Mississippi, evidently, but it has very southern voting behavior. I haven't kept track of how long I've been talking about this scatter plot, but this has probably been about 5 minutes on this particular overhead, and we still aren't done talking about it. Scatter plots are full of information, interpretation, and insight, and this particular scatter plot is no exception. Very informative, lots of information here. One last thing I'd like to say about this scatter plot is the 1980 election was the first presidential election I was able to vote in, and I did not vote for Jimmy Carter or Ronald Reagan. There was a third-party candidate that was running for president in 1980, and his name was John Anderson. And so I'm happy to report to you that me, your instructor, John Anderson, voted for John Anderson for president in 1980, and it's been one of the greatest decisions that I've made. I've never regretted voting for John Anderson for president. In fact, if you can ever vote for your own name for president, you should do it. It's a great source of amusement for your entire life. Here's another scatter plot, and this one is the first one we've seen, I think, that shows a negative association. In what's being graphed here, well, we have states. The points represent states in the United States. The horizontal axis is the percentage of students, high school students in that state that take the SAT college entrance exam. And the vertical axis is the average score for math part of the SAT. And so what you can see is that as the percentage taking the exam goes up, the average score, the average math score, goes down. This direction is a negative association. It is not linear. It looks like there's some pretty clear curved nonlinear pattern, and there is just a moderate amount of scatter. It's a pretty well-defined nonlinear pattern. Why is this happening? Well, if you think about it, why would let's go back down here to states that don't have a very high percentage taking the SAT. These are states that are going to be in the Midwest that are going to typically be taking the ACT exam. And so why, Minnesota, North Dakota, whatever, why would students in these states ever take the SAT? Why would they take the SAT? Well, because they're trying to go to an elite school that requires the SAT. So, Harvard, Stanford, University of Minnesota Morris, elite schools like that. And so those are going to be the students that are going to be taking the SAT. Do you think those students will be very good at math? Well, it turns out they are very good at math. And their average math scores are very, very high because it's only the very best students in the state that are taking them. Out here, these are states where pretty much everybody and their bubba is taking the SAT exam. And with all of those students taking the SAT, many of them of sort of low ability, driving the average math score down. It's not a selected cream of the crop taking the exam. It's sort of everybody and their bubba taking the exam and moving the average score lower. You can see that Georgia and North and South Carolina are particularly low, even compared to what we would have been expecting from their state percentage. Here's the same kind of relationship, just in a different year, and you can see some of the states that are highlighted. Here you can see that North Dakota is up here at the top, the highest average SAT scores for math. There's probably 6 to 10 high school students in North Dakota, and the 3 smart ones are taking the SAT and they score really well. I'm exaggerating, but that is the essence of why North Dakota is so much higher than any of the other states. Very strong selection. Here is another slightly different graph in a different year, and you can see each data point highlighted. Here's Iowa, South Dakota, North Dakota, Nebraska, Minnesota in here. All these ACT states with very selected groups taking the SAT, scoring very high on average. And you can see these states out here that are very much SAT states, scoring notably lower because everyone's taking the exam, not just the smart students. South Carolina, particularly disturbingly low score here. Here's a scatter plot for a wind turbine that's here at the University of Minnesota Morris, generating electricity for our campus. Here's the relationship between the average wind speed on a day and the amount of energy produced by this wind turbine. And you can see the general pattern of positive association. The more wind, the more electricity produced. That's a positive association. You can also see that there's sort of an S shape here, a nonlinear shape. This is not a linear pattern, and that the scatter is very concentrated and not a lot of scatter around the pattern. Let's try to understand what some of this means. Points that are down here at low average wind speeds, of course, if there's not very much wind on particular days, there's very little electricity produced on the vertical axis. You'll notice there are some days out here where there is a lot of wind but no electricity produced, and I believe the turbine was broke and being repaired on those days, and so no electricity was produced. The other thing maybe to notice about this is that when we get up to very high average wind speeds, the electricity produced basically stabilizes and flattens notably, and that happens because when wind speeds get too great and too much wind, the wind turbine shuts off and protects itself from damage. And so that's basically what's going on here. Here are some different scatter plots with some different scaling mechanisms to watch out for. Basically, anytime you see scatter plots that have a lot of white space, like this one here in the top row in the first column, or the top row second column, or even this one down here, a lot of white space typically is a sign of a misleading scatter plot. You're going to want to have scatter plots that are more like the one here in this lower left corner, without an excessive amount of white space. This first one sort of looks like there's almost no relationship between the x and the y variable. The one here in the upper right looks like there's a very drastic negative linear association. The one in the lower right sort of looks like there's almost no relationship at all. And it's all because of the scaling of the measurements. You're going to want to produce scalings more like the one on the lower left to avoid producing misleading scatter plots. If you ever see scatter plots with a lot of white space like this, they're improperly constructed, and you might suspect you're being manipulated and you're trying to, the author of the plot is trying to manipulate the impression presented by the plot. What we're going to work on next is strength of the relationship. And so in the left-hand display, there's a very strong positive association between x and y, and a less strong relationship in the right graph. This is the concept of strength of relationship. You can see the same sort of thing here in these two graphs. The graph on the right is a much stronger positive pattern than the graph on the left. There's more scatter, less strength, less strong relationship. The way that we typically measure strength of relationship is through the correlation coefficient, little r. And this is a very complex formula that is being used when we have our statistics package computing this for us, but the correlation coefficient involves the pairs of measurements and how they move together in the scatter plot. Correlation coefficient is a number, and it runs between -1 and +1. -1 means there's a perfect downward trend, straight line. A correlation R of +1 means a perfect upward positive association. Correlation is symmetric. It doesn't matter which variable is x and which variable is y. Correlation doesn't have any units. It doesn't have a unit interpretation. It doesn't depend on how the variables are measured. Changes in the measurements of y and x really don't change the correlation coefficient. And it's good to know that correlation is measuring the strength of the linear trend, upward or downward. If there are nonlinear trends, correlation doesn't measure that. Correlation is also very sensitive to outliers, and we'll see examples of that where a single data value can really artificially inflate or deflate correlation. In overhead 27, here are a few scatter plots and the correlations for each of them provided. So in the upper left, we have a scatter plot that has a correlation of 0. There's really no discernible upward or downward trend in this graph. The upper right scatter plot has a very weak downward trend, and it's weak, and the correlation value is fairly close to 0. It's a negative value, a -0.3, and it's a negative pattern, but very weak. As opposed to this one down here in the lower right, where it is a very strong negative pattern. Almost a correlation of -1, -0.99. Remember, the smallest a correlation can ever get is a -1. Right next to it here in the lower left is a correlation that's almost a +1, 0.9. And some other values as well. What we need to have you do is look through these examples and try to visually understand how a scatter plot connects to a correlation number, and use this as a template for calibrating your thinking, because on exams you're going to have to be able to specify a correlation just based off of the visual scatter of points. You don't have to do this perfectly, but you have to do it reasonably well within a ballpark. And so here are some further examples of that. Here are some other correlation examples just to give you more ability to understand different patterns and what the number is that goes with it. On overhead 29, we have a scatter plot of points. Please don't be thrown off by the 2 and the 3. These are just telling you how many plot symbols are trying to occupy this location. I would give you a graph like this, and I would have you try to come up with a correlation. This is a pretty strong upward positive pattern. You're going to want to pick something that is a bigger correlation but positive. The actual correlation for this one is 0.613. This is the actual correlation for this pattern. I probably would have accepted a correlation as low as 0.45 and maybe as high as 0.75. That's how close you would have to be to this truth. Here's another one. This one is a very weak negative trend, so you're going to want to have a smaller negative number, like negative 0.237. I probably would have accepted something as negative as negative 0.5 and maybe down to about negative 0.1. Now, negative 0.4 down to negative 0.1 would have been acceptable for full credit. Here's another much stronger positive association. You're going to probably be thinking about something like about 0.9 here. Well, 0.891 is the truth. I probably would accept something between about 0.8 and 0.95 to be in the right ballpark for full credit. Here are some other scatter plots that all have a correlation of 0.7. And you can see that like up here, there's a blob of points with one real wicked outlier up here in the corner. And even though this is not a very clear pattern, if you computed the correlation number, it would be at 0.7. Over here in the upper right is a very strong linear pattern with one point off out on its own, and this would cause the correlation to be 0.7. Here are two blobs of points arranged in such a way to give 0.7. The point of this overhead is to get you to make sure you graph the data before you calculate a correlation and try to use it as a trend. Please be aware that when you have curved relationships, correlation doesn't measure strength of a curved pattern. It only measures strength of a linear upward or downward pattern. And so here we have almost a perfect nonlinear relationship, but it's only slightly linearly negative. And so there's kind of a weak correlation, even though there's a strong pattern. Same with the middle diagram as well. So please be aware that you need to look at the displays before you quote correlations. Here's an example of doing this with our blood alcohol content data. I've graphed them here, and I've put a trend line through the points, and we use the COR command for the two variables BAC and beers, and the correlation here is quite strong, 0.894. Remember, correlation can only get as big as 1, and this is almost as big as it can get. And not surprisingly, blood alcohol content is very strongly connected to the number of beers you drink. Finally, we're going to talk about growth curves, and you can chart the length of a child in inches on the vertical axis, response, and age or time on the horizontal axis. And so this part of the display up in here is for the height of a child over time, and for this part of the display is the weight over time, and the weight is measured in pounds over on this right axis. And so here is a particular set of growth points for a child, and at birth, right down here, B for birth, times 0, the length of the child is measured over here on this axis in this part of the curve, and what you can see is that at birth the child is quite low in length. If we go back to the other curve, maybe we can see this better. The lines, the middle line represents the 50th percentile for length. Half the children are lengths longer than that point, and 50% are shorter than that point. The upper boundary is the 95th percentile, and the lower boundary is the 5th percentile. And so normal height or length is between these two boundaries. Same for weight. Back to the child in the next one, you can see that at birth, this particular child is a very low length, and in the next month gets a little bit longer relative to the 5th percentile, And then finally, after 1 year, 12 months, this particular child is at about the 75th percentile for length. For weight, the child starts out at birth, small birth weight, and eventually grows on the weight axis at 12 months to probably about the 25th percentile. So at about 1 year of age, this particular child is much longer than typical and is lighter than typical, long and thin. And if you have ever seen me, you will know that I am tall and thin, and that this was the growth pattern for one of my offspring. Let me know if you have questions.